Okay, so this is a pretty major topic, but we're just going to scratch the surface today. And that is the physical representation of this antiderivative integral thing we started talking about on Wednesday. So you'll recall, well, hold on, let me go through the slides, because otherwise I'll just, okay, so yeah, that, and then, okay, that, great, and then, okay, and be able to draw that squiggly integration symbol so that it doesn't look silly. Anybody perfected that yet?
Yes.
Excellent, good. Okay, so this is what I was getting to. When we talked about derivatives, we know that derivatives represent three different things: slope of the tangent line, rate of change, and the velocity, right? Instantaneous velocity. The blue is what we're going to use for the purpose and or representation of the integral. Okay, so the integral of function represents the area under the curve. What does that mean? Well, if I've got a function, let's suppose, I don't know, we'll take something like the square root function. The integral is the area out to a certain point. Let's say here, we'll call it b. The integral of the function is the area between the function and the y-axis. It's just that simple. However, we don't know how to do this yet. So we're going to cheat. And we're going to cheat by making a bunch of rectangles. It's a rectangle, Eric. I'm not asking you to create an octagon.
There's so many rectangles.
There isn't a single rectangle up there. You're like Eeyore from Winnie the Pooh. No matter what miserable, simply miserable.
I'm not. This is really. I thought I loved this one.
Okay, so the red is our function. The purple are the rectangles I'm going to use. This is garbage. Why?
Because there's all that empty space.
Perfect. There's all this wasted space. In case you can't see that, Lily's referring to that, this, and that guy. So we won't get a very accurate representation. But that's okay, because this is how we're going to start. Let's suppose I was going to do this again. How could I cut down on the wasted space? Got it?
You could find the 2 points. So you have your time frame right here.
Yep.
You find the 2 points and the middle one. So you have like a trapezoid looking thing.
Ooh. If I'm understanding you correctly, you're saying do this?
Yeah.
Well, that would certainly cut out a lot of wasted space. And in fact, that's such a good idea, we're going to give it a name. It's called the trapezoid rule. We'll get to it later. Well done. How else can we cut down on the wasted space?
Smaller trapezoids?
Stay away from trapezoid. He's already done that one. But you're on the right track. Smaller
Shapes? Rectangles?
smaller rectangles.
Shapes?
Yeah, shapes.
Octagons.
Little duckies. Smaller rectangles, skinnier rectangles, would put the, so if you imagine instead of having what we have here, you go something like this. Why is it taking so long to draw here? Something like that. And you would get less wasted space. Hopefully you realize that if we shrink the size of the rectangles, the number of the rectangles will go up, yes? Mm-hmm. Those are the same thing. Increase the number of rectangles. Increase number of rectangles. Or decrease size of rectangles. Try writing when you can't see what you're writing. All right. That's not even legible, but we'll go with it. Okay. So all we're gonna do is start by approximating, these are approximations, the area under the curve by using rectangles. Whoops, wrong way. Let's get some terminology under control here. Wherever we start is commonly called A. It won't always be the origin. Wherever we end is commonly called B. Okay, starting and stopping point. Therefore, B minus A will be this entire length. Are you with me? Good. Based on that, how wide is each rectangle? In terms of B and A. Why is this so challenging?
Is it a thing on the notes here? B
I don't-
minus A over N?
Oh, great. I could teach a second grader to do that.
I was gonna guess that, actually.
Uh-huh.
That's funny.
Why?
Because it's the space divided by the number of rectangles.
Yeah, in this picture, I'm going from 0 to 10. There's 5 rectangles. 10 minus 0 is 10 divided by 5 because there's 5 rectangles makes each one equal to a width of 2. Okay, that width, which is represented here as the width of one of the rectangles, we'll refer to as delta x, the change in x for each of them. Initially, we're going to start problems where delta x is constant. You calculate it once and you stay with it. Later on, we're going to change that. We'll talk about that later. That's a more conceptual thing. Question?
Are the rectangles always going to be the same width?
Great. That's what I just said, yeah. So yes, for us now they are. Later on, we're going to change that when we get into something called a Riemann sum. But that's not till after break. So we can just count, we just do rectangles. Okay, so if I look at this picture, let me get rid of all this mess. I think I can pretty much do the whole lesson off of this one picture. If I want to approximate the area under this function, let's call the function f of x. I just need to find the area of all 5 rectangles and add them up. Are you with me on the concept? Good. And we know already that delta x is 2. We did that calculation, right? We need 2 things for the area of a rectangle, the base and the height. How tall is this first rectangle? 4. Now you know that because I gave you, or you can see it right there on the y-axis. Let me change the color so you can see it purple. Therefore, that has an area of 8. Easy peasy. Here's the fun part. What about that rectangle?
4.5.
It looks like it might be 4.5, but you don't know that. How would I be able to calculate exactly how tall that rectangle is? The process involves something like this. I look at this rectangle and I see it's touching the graph right there. So I need to know the f of x value at that point. That point is at 2, because delta x is 2. Therefore, the height of this rectangle would be f of 2. Does that make sense? It's the y value. You get the y value by plugging into the function. Now, if this is put on a nice coordinate plane where you can see exactly where that's at, great. If they don't, or you don't have it that way, then you calculate the height of that rectangle by taking the value at that point where it touches the graph. This third rectangle, for instance, hits here at 4, so the height of this would be f of 4, f of 6, and f of 8. Okay, you with me? Is this a difficult concept? No? Good. So then I don't want to beat a dead horse. I do want to get into the 4 different scenarios, though, that you're going to run into with the rectangles. They're pretty easy. It goes something like this. Okay, yeah, I got that. Okay, we did that already. Great. Okay. Now, notice, in the purple one, if I pick any one of those rectangles, the right-hand side of the rectangle, the left-hand side of the rectangle is what touches the curve. Okay, so if I take this rectangle, for instance, if I take this rectangle, for instance, I go up the left-hand side of the rectangle to see where it touches the curve. That's called, strangely enough, a left-handed rectangle, as it says right there. you can pretty much figure out what a right-handed rectangle looks like. It's when the right-hand side of the curve touches, or right-hand side of the rectangle touches the curve. Are we good? Okay, let me give you the graphic, blah, blah, blah. Right-hand rectangles. Go back to purple picture. When I calculate the area of those 5 rectangles, this seems like a silly question, but I'll ask it anyways. Will the answer be smaller or bigger than the actual area under the curve? Smaller. Good. Perfect. In this case, when I do a right-hand rectangle, is the area bigger or smaller than the actual area? Bigger. Good. Okay? Those are called overestimates and underestimates. What I don't want you to do is relate this always being the case. Left-hand rectangles are not always underestimates. Right-hand rectangles are not always overestimates. It depends on the shape of the curve. This happens to be an increasing concave up function. If it's different, like it's decreasing, or it's concave down, things might change. So the best way to attack these problems is to graph them, draw pictures, and calculate areas. Okay? So let's do this one together. Now in this case, I gave you f of x. It's a parabola 1/2 x squared plus 2. We're going to use 3 rectangles. Question number 1, what's delta x? Matthew, are you raising your finger at me?
The answer.
Thank you for using the appropriate finger. Go.
Oh, okay. We use b minus a over the amount of rectangles we want to use.
Mhm.
So b is 4 and a is 1. So 4 minus 1 is 3. Over 3 rectangles is 1.
You had me scared there for a second. Okay, so we're going to keep it simple. I'm not starting at the origin, I'm starting at 1. Going out to 4. I don't want to repeat what Matthew said, but we got delta x now. Go ahead.
Are you always going to be given a picture?
No, not always. Sometimes you'll have to draw it. Okay. Now here's how I approach the problems. I know I'm going to get 3 rectangles. I'm going to start at 1. I'm going to end at 4. And I have 3 rectangles. So I have 1 there, 1 there, 1 there, and 1 there. So I draw in the vertical segments first. Now why do I do that? Because now I can make the decision, am I going to go right-hand rectangles or am I going to do left-hand rectangles? Okay, and this one says to do both, so we'll do the left-hand rectangle first. How do I do that? Well, I take this first rectangle, I go up the left-hand side of the rectangle. When I hit the function, I come over and make a rectangle. Okay, here's rectangle number 1. Second rectangle, I go up the left-hand side of the rectangle, come across. I have my second rectangle, Roman numeral 2. Go up the left-hand side of the third rectangle, come across, rectangle 3. Have I lost anybody, or are we good to go? Beautiful. That's the hard part. The rest is easy. What's the area of rectangle number 1? Well, I know it has a width of 1. How tall is rectangle number 1? It doesn't fall on a nice value, so where am I going to get the height of rectangle 1? It's going to be 1 times f of 1, which is, f of 1 is 2.5. I plugged 1 into f of x. I'll leave that there for a second. Area 2 still has a width of 1. Now it has a height of f of 2. And f of 2 is 4 times a half is 4. Last but not least, area 3 1 still times f of 3, 9, 4.5, 6.5. Therefore, the area would be 10.5, 13. Overestimate or underestimate? Underestimate, right, because we got some wasted space between the function and the rectangles. Anything tough about that? No? Okay. If I'm doing a right rectangle, exact same procedure, except I go up the right-hand side of the rectangle, come up, go across, oh, come up, go across, come up, go across. From the picture, you can see I'm going to have an overestimate. I have some different heights there, but still doable, and you just go and find the area of each of those rectangles and add all three up. Good? Okay. That's the first two types, left-hand and right-hand rectangles. Question?
Okay, maybe this is a silly question.
It's not a silly question. The only silly question is the question never asked.
How would the heights be different? Like, I see that they go, like, higher, but if you plug, like, the, x value into the f of x.
That's not a silly question. That's a great question.
Okay.
Look at this. You get the blue rectangle, right?
Yeah.
So the blue rectangle is touching on the left-hand side, which happens at 1. This red rectangle now, this red rectangle touches on the right-hand side, and that right-hand side is actually at 2.
Okay.
So the area of that first rectangle would be 1 times f of 2. So the weird thing is, and this won't always happen, but notice that the first red rectangle has the same area as the second blue rectangle. And that process continues.
Okay, thank you.
Okay? Not a silly question. Any other non-silly questions? Any silly questions? Okay, just checking. Yeah. Oh, look, I had pictures already. Boy, I did way too much work. 13, is that what I had? Oh, good, I feel good about myself. And then you do the right-hand rectangles. We should get a bigger answer. 20.5 bigger answer. I'm happy. Okay? Right hand, left hand rectangles. When the shape of the curve changes, I'm like a bull in a china shop. Anyways, when the shape of the curve changes, you might get a little bit different setup, but it doesn't matter whether it's increasing, decreasing, concave up, concave down. If you just take your time and draw careful rectangles, you'll be fine. Okay? Left-hand rectangle, right-hand rectangle. Last two types is upper and lower sums. What that means is, let's back up. When you do a left-hand rectangle, you're always going up the left-hand side of the rectangle. When you do a right-hand rectangle, you're always going up the right-hand side of the rectangle. These two are different. Upper sums means you're always above the curve. Might be left hand, might be right hand. You draw whichever rectangle you need to make the rectangle go above the curve. Lower sum, always below the curve. Unlike the left-hand and right-hand rectangles where those things can change, an upper sum is always an overestimate. A lower sum is always an underestimate. So these are a little bit more difficult to work with because it's not as algorithmic. At some point you have to do a little bit of thinking and seeing, do I go from the left over to the right or from the right over to the left? So we get something like this. Okay, so you look at this pseudo-cubic function here. I have some rectangles, like the ones over here, that are left-hand rectangles because they're hitting the curve on the left-hand side. But then as I jump over here, all of a sudden they become right-hand rectangles because they're hitting on the right-hand side. So you pick whichever one it takes to guarantee that your rectangles stay below the curve. Question, Luke?
Is it possible for it to like hit in the middle, like not left or right?
Ooh, it is, yeah.
How do you do that?
Cry. You can see, like, it's pretty rare, but sometimes we'll talk about something called a midpoint rectangle. So it would become something like a midpoint rectangle. Okay. Depending on your curve, maybe your curve is constant, so you have a horizontal curve. Then it's just a straight up rectangle. But I wouldn't worry about it now. We'll deal with that later. Okay, so we jump over to the right-hand side of the picture. Those rectangles are all designed to stay above the curve. So again, some left-hand rectangles, some right-hand rectangles, whatever it takes to make that happen. Notice the notation. Underestimates use a lowercase s. Overestimates use an uppercase s. S standing for sum. Now, to make matters worse, depending on what source you're looking at, they will also use the term inscribed or circumscribed. I don't know why. It's like local max and mins being the same as relative max and mins. Somebody decided they want to call them upper sums. Somebody else decided they wanted to call them circumscribed sums. But in case those terms pop up, you know what they are. We're doing okay for time. Yeah, so there's the inscribed, circumscribed. We're good to go. Okay. I'm not going to do this one because A, I'm concerned about time, and B, it's not much different than what we already did. In fact, it's the exact same curve. Okay, the only difference here is you would have to decide what to use, and in this case, they would all be the same because of the shape of the curve. And we're done. Okay, questions? Good. Don't make this more difficult than it has to be. All you're doing is creating rectangles. Take your time.